It is my pleasure to introduce John Willis, our speaker today, who is an emeritus professor of theoretical and solid mechanics in the University of Cambridge. And he has held full-time positions before at the Imperial College London, the Courant Institute in New York, Cambridge, Bath, and then again back to Cambridge. He was also professor of the Mécanique at Ecole Polytechnique for 6 years from 1998 to 2004. And he has achieved a lot of honors during his career, some of which being elected the Fellow of the Royal Society in 1992, Foreign Member of the US Academy of Engineering in 2004, Foreign Associate of the Académie des Sciences in 2009. He was the editor of the Journal of Mechanics and Physics of Solids from 1982 to 2006. And recently his research work has focused on strain gradient plasticity and waves in metamaterials. John, please.
Okay, thanks very much. Now I can't even see myself now because I put that icon out of the way. So I just hope I'm still in contact. I guess I am.
Yes.
I skipped over by accident, actually, the title page of my presentation. So you see the first slide that I intended to show. And what you see there is my attempt at drawing a random medium. Look, I made a big cursor too. This is supposed to be a random medium. It's just a matrix with some blobs on it, put down at random, and they square blobs because I could do that. And this thing underneath here is a homogeneous medium. They're bonded together. The random medium, if you like, was infinite, but then I cut it in half, notionally. That's because I want it to be sort of statistically uniform. I cut it in half and stuck that homogeneous half space underneath. Now, it's jolly hard to get this cursor. This red arrow here is supposed to denote, this set of red arrows are supposed to denote an incident wave. There's a green one, which is a reflected wave from that interface, and there's a brown one in the random medium, which is a transmitted wave. Now, actually, what we should be looking at is a real mess with multiple scattering. But what I'm just trying to sort of indicate there is the mean wave. That's to say the, excuse me, the ensemble average of all of these waves, or what is often called the coherent wave. And that's what I'm going to be pointing towards in the end. Now, as far as the talk is concerned, first of all, I'm going to focus on the random medium without thinking about the half space, the homogeneous medium underneath it. And I'll just sort of formulate how to deal with it and sort of discuss its properties in a moderately general way. But then I'll sort of successively specialize until I get down to this very problem, and not only this problem, but actually a somewhat special case of this problem that I've managed to solve completely explicitly. I believe that effort is worthwhile because there's been huge interest in waves in media, heterogeneous media, usually periodic, but also random, because of the surge of interest in what they call metamaterials. But you try putting a boundary on one of these things, like the interface that I've shown, and it seems to me that almost nothing is known. And I certainly knew that I didn't understand much about it myself. So I thought I'd look at a simple case and try and analyze it and see whether I could extract any general features from it. Well, I haven't managed to extract any general features from it much. I'll say what I can at the end, but at least I've solved the problem. And it's maybe one of possibly two solutions that exist at the moment. In some respects, this is the more general one. In some other respects, maybe another one is. It's not to do with me. Now, the context is this. I usually consider elastic media, as you know, and so I'm going to talk about elastic media. But of course, the structure, the mathematical structure, applies also to other situations, and in particular to electromagnetics. But what you're going to see today is elastic media, but even so, a rather particular thing. Now, in the middle of this screen, you see the equations of motion, divergence of stress plus body force equals rate of change in momentum, then some constitutive relations and kinematic relations that define the strain, and also the velocity is just u dot. Okay, so u is a vector, sigma and e are second order tensors. But when I come around to do some calculations, I'm going to simplify it by reducing this to a sort of scalar version of elastodynamics, in which u becomes a scalar. So E is no longer the strain, it's actually the gradient of displacement u. U is just a scalar. Stress becomes a vector. And if the medium is isotropic, which I'm trying to get my cursor again, can't find it. Yes, got it. The constitutive relation is going to be the one you see there. Sigma equals just a constant times gradient of u. Now, just remember those equations for a second, because on the next slide, the first thing in red is what you get if you just express that whole those equations in terms of this scalar displacement u. And you see it looks just like elastodynamics, except u is a scalar, not a vector. Now, I'd like to say this. Although this is an analog because it suits me to deal with this because I know elastodynamics much better than anything else, let's talk about regular acoustics in a fluid, heterogeneous fluid. Well, usually there, well, the scalar is P, the pressure increment. And U is a displacement, but that's going to be a vector, of course. And the constitutive relation is in the middle of this slide here. P equals minus kappa times the volume change, div U. And the equation of motion is minus the gradient of P plus body force equals mass times acceleration. But if you put those things together and get an equation for P, it's the thing that's in this second red box. And if you look at the second red box versus the first red box, you'll see they're just the same, except that mu is in the place that 1 over rho is in the second, and so on. And rho in the first is like 1 over kappa in the second. And of course, the boundary conditions or interface conditions are continuity of pressure and continuity of normal component of displacement, which is basically the same conditions that I would have as in elastodynamics. So now what I'm going to do, I'm going to continue with the full elastodynamic system, not just this scalar version of it. They look more or less the same anyway. And afterwards, I'll do the specializations. Right, so here we go. Now, first, I'm going to get rid of time by Laplace transforming, so that d by dt is just going to be s, okay? And it's nice for me to think of s being real, because if s is real, I can write down the Laplace transform equation of motion, okay? And I can write down a variational principle that is equivalent to it. It's in that red box that you can see. V, of course, is S times U in this formalism, okay? And if S is real, that's a minimum principle. If you wanted to go back into the time domain, the products would become convolutions, and I'd be back to something that Mort Gertin did 40 or 50 years ago, middle of last century anyway. I'm going to carry on talking about minimizing as though S is real, although of course it's also possible for S to be complex, and if it is, the minimum principle only becomes a stationary principle, but it's still a variational principle. Okay, so there we are. Oh, this slide says just the same as the first one, except of course you see the green stuff that's come on, where I've defined sigma 0 and P0. Now those are any stress field and momentum density field that satisfy the equation of motion and any conditions on tractions and body forces which are given. Okay, so they solve the they solve the equations of motion, but they don't satisfy any constitutive relations whatever. They don't have to be related to any strain or velocity or anything. Okay, so there we are with that. A bit of notation for the sequel. I like to write down sort of matrices. The straight L that's in this box is elastic moduli, so that's a fourth order tensor if you like. And rho here, it's a scalar, except it operates on a vector, so morally speaking, it's actually a second order tensor. And then there's no coupling between stress and velocity, yes, there's no coupling between stress and velocity because of the zeros off the diagonal. Okay, so that's a notation, and if I use that sort of notation, this energy-like functional here is going to look the way that I just written it, and you can see. Okay, now then, suppose I've got a random medium. Well, if I choose any particular sample, it's described exactly in the way that I just have, except, of course, that each sample has a label alpha, and it's chosen from a sample space, whose properties I don't really want to mention to you. It's a detailed technicality which is of no practical interest here. Okay, but nevertheless, that means if the variational principles also got a label alpha, and I minimize, I get the solution in realization alpha. But I can pick up the solution for every alpha if I require that the ensemble average of that E of alpha is itself minimized with respect to all displacements now, which don't only depend on X and S, I don't write that, but also on alpha. So now what I want to do is consider doing this sequentially. In the middle of this, I say so. First, let's minimize the ensemble average of V, subject to the constraint that the ensemble average of U is prescribed. It has to satisfy any boundary conditions on U that are given, but otherwise arbitrary. And after I've done that, minimize the result with respect to the ensemble average of U. Well, if I do the first minimization, I get what you see in the second oblong red box, okay? And you see, it's pretty obvious it's got to happen this way. I'm going to get a quadratic form in the ensemble average of E and V, okay, coming from U, minus sigma 0 and P0 times the average of E and V rather than just E and V. When I ensemble averaged the original variational principle, of course, I had E and V in that slot, and they've just come over to be the ensemble averages directly, so they don't participate. Now, there's a statement here at the bottom that actually the L effective that I've just defined actually does deliver constitutive relations, effective constitutive relations. I've said there, and it's true that. You can see what I've claimed. And the next slide is just going to tell you that that L effective thing is independent of the sigma naught and P naught. In fact, as I've prescribed the mean value of U, then I'm going to have to choose a sigma naught and P naught that would deliver it. But this is the way it is. By the way, I'll say this now, these effective constitutive relations involving L effective are not unique, because it's possible to change the L effective to something else and get exactly the same answer for the constitutive relations. You can't do this with local relations, but with non-local ones, there's this inevitable non-uniqueness. So in effect, there's an equivalence class of operators L effective, if you like to think of it that way. Okay, now I'm going back. Almost all of this slide is a reminder of one a couple of slides ago. The only difference is the bit at the bottom. I've introduced a Legendre transform, and you can see this. There's new variables. There's Tor. Okay, I'll talk about Tor. Tor, L minus L0 inverse times Tor plus Tor times E. And if I made that stationary with respect to Tor, I'd get back to E times L minus L0 times E. So the L0s would cancel out and I'd get back to L. Okay, and similarly for the rho thing with pi. I've introduced things like this before. Tor is actually usually called the stress polarization. I think Hasheen use that terminology first. And I've called that pi the momentum polarization because it's related to the momentum. Okay, now, here's the statement. If I make H stationary with respect to torn pi, I reproduce the original E. You could see that. Okay, likewise for a random medium, if I make the ensemble average of H stationary, okay, with respect to random fields, tor and pi, I'll reproduce the ensemble average of the original thing, energy function curly E. Okay, but first, what I'd like to do is to minimize that ensemble average of H with respect to the field, the stochastic field U of X and alpha. If I do that, it's going to happen in every realization. I can get, I've just put something down on my screen. That's okay. I get this thing here that you can see. U is U0 plus the Green's function for this comparison medium with properties L0 and ρ0. Okay, U0 plus the Green's function G0 operating on the divergence of tor minus pi dot or S times pi if I'm in this Laplace transform configuration. And there's also a contribution from the boundary value of tor dotted with n. But what I want to do next, I don't want to write it. I want to integrate by parts. I also want to differentiate either with respect to x or with respect to time to get the relationship that you see right here, okay, where I've written out one of these components of S. I've written out S suffix XX. You can see it. If I write this equation symbolically, I've done it in red there, red box. There it is just looking like a matrix. And that curly S thing is the matrix with S's that's written previously. Okay. And if I take hold of, God, it's hard to get this. If I take hold of this and ensemble average it, I get the relationship I'm pointing at now. And then I can eliminate E0 and V0 and get the thing that's written here. And that thing, you see, has no information about E0 and V0. Hence, it has no information about the things that drove it, sigma 0 and P0, okay? And it actually gives me the minimizer conditional on prescribing the ensemble average of U. That's what it says there. So what I want to do now is to take hold of this representation here, okay, this one, the conditional minimizer, substitute it into that ensemble average of H. And if I do that, I get what you can see now across the top half of that screen. And what you see is a quadratic form using L0 and P0 and sigma 0 minus a quadratic form that involves tor and pi. There's a quadratic term, two terms of that, and a linear term at the far end of it. Now I try and make that stationary with respect to tor and pi. I don't know how to do it because this is a random medium, but nevertheless, the stationary point should exist. It will exist under suitable conditions, of course. And the values of tor and pi that make the expression stationary will be related linearly to the driving terms, which are ensemble average of E and ensemble average of V. Okay, and what the stationary value is going to be is actually 1/2 of the thing that comes from the linear term in tor and pi. So I've written it out here in short notation using this formal curly T thing that I don't actually know. But now what you see, is an expression for L effective. So that's sort of theory, exact theory, if you like. The trouble is I don't know how to find curly T, but I can find an approximation of Hessian-Strickman type, okay, kind of thing which I've first did many, many years ago in the middle of last century. And that's what I'll talk about next. So what I'm going to do now is I better tell you about the medium first. L is going to be LR. This is an n-phase material. And in phase R, the elastic constants are going to be LR. And the characteristic function of the region which is occupied by material R is going to be chi R. And a similar thing for the density rho. And what I'm going to do is to seek an approximate stationary value of this ensemble average of H for this medium, okay, by taking Tor in this simple form. It shouldn't be that simple. This is a very particular form for Tor of X and alpha, but it's going to give me an approximate stationary value which only contains information which I stand a chance of knowing. So I don't know that it's easily possible to do very much better than this. It's only going to be an approximation. Actually, incidentally, also if S is real, it'll give me some bounds. So at least that's something that's kind of rigorous about it. Well, if I go on, I better tell you now, if I substitute that approximation into my equations, the things that will turn up will be the ensemble average of this correlation, of this characteristic function, which is the probability for finding material R at point X. And there'll be a product of these things, you see it here, P, R, and R dashed. And this last thing here is going to be essentially a sort of a covariance constructed from the P, R, and R dashed. It's just got the sort of average value subtracted off it. And with those definitions, if I put those into the, put this approximate stationary field into my expression, I get the thing in the big red box at the bottom. Okay, so there you see it. There's a quadratic term. There's another quadratic term. I'll define this on the next slide. And there's a linear term. So it's sort of like the static, except of course it's approximate. The thing I said I define, it's an integral operator over the domain omega. And the kernel of that operator is what you see, S of X and X primed times psi R, R primed of X and X primed. Now, suppose the medium's infinite and it's statistically uniform. If it is, that operator, S psi, is going to be a convolution operator. If the kernel is only going to depend on X minus X dashed, okay? And the equations defining Tor and pi can be Fourier, the equations defining those equations can be Fourier transformed. And then they become a system of algebraic equations. Furthermore, it's fairly easy to solve these equations in the special case that the medium's only got two phases, n equals 2. The reason for this is because when n is 2, there's basically only one independent psi. And you see, I like to write this as P1 times P2 times H. The reason for that is that when X minus X dashed is 0, H is bound to be 1. And also if X minus X dash gets big, and if the composite's got no long range order, H will tend to 0. Okay, so there's only one thing to choose. Also, the equations themselves can be manipulated into the form in the square box on this next slide. Okay, the term that I called H0 here is defined here. It's S times H. It came from S times psi, but I've taken out the P1, P2 factor. L hat here is also a funny one. It's P2 times L1 plus P1 times L2. And what angle square bracket Tor means is Tor 1 minus Tor 2. And what angle bracket Tor means is P1 Tor 1 plus P2 Tor 2, and so on. Well, the first equation only involves the jumps in Tor and pi. So formally, at least, we can solve it. And the solution's written out at the bottom there. Okay, if I'm Fourier transforming, this is just matrix algebra I'm talking about. If it were in real space, of course, this would be operators. Okay, and then of course I can substitute the square bracket Tor and pi into the second equation, and I can get an expression for the ensemble average values, and it's here. And what's in curly brackets, in effect, must be this this approximation to the exact operator curly t. And so immediately, if you can remember this far back, I've got myself an expression, an approximate expression for L effective, and it's there in the middle, okay? I'll try and make just a remark about it. It's pretty much inevitable from this, from both from the approximation, which is explicit, you can see that tau, average of tau is going to be coupled not only to E, but also to the average of V. And pi is going to be coupled not only to the average of V, but also to the average of E. This means that that L effective no longer is going to be a sort of a diagonal object. It's going to have peculiar couplings. It's going to have coupling between stress and velocity as well as strain, and between momentum density and strain as well as velocity. That doesn't mean there aren't more derivatives involved, but that's the way it is. So that's the basic theory, folks. Now I'm going to specialize it to acoustics, because there's still work to be done. And I'm a little bit ruthless here because I'm going to consider a medium. It's an acoustic medium, so it's only got a sort of a modulus, one modulus mu, but I'm going to choose that to be the same for each material, two of them, okay? But I'm going to have the density, okay, taking value ρ1 in material 1 and ρ2 in material 2. That's all. Now, in this case, the effective response operator is bound to be that the stress is mu times the strain, or grad U, okay? And there's going to be no cross-coupling, and there's going to be just that the momentum density is ρ effective times the mean velocity, okay? That's the way it's going to be. And if I specialize that formula for L effective to this particular situation, it comes out to look like this box here, okay? There's a slight cheat here. It's partly because I didn't think carefully enough when I constructed this notation. H0 has changed from being what it was before to being just G0 times H, whereas it should really, originally, the way I had it defined before, it should have been S squared times G naught H. And now you see the factor S squared coming in explicitly here. The reason for that is that now I can cut and paste equations from stuff that I've published. Okay, so that's it. So that's ρ effective for you. I'll make a remark. I mentioned previously the possibility of getting bounds. If ρ0 is the bigger of ρ1 and ρ2, I get an upper bound for the effective ρ, and a lower bound if ρ0 is the smaller of ρ1 and ρ2, so long as S is real. Now, for the scalar problem, I need the Green's function. Well, the Green's function's easy. It's written out there, okay? Its Fourier transform is also dead easy. It's written out there. Now what I'd like to do is to adopt, this very special correlation function, e to the minus r over a. It's not completely unreasonable. It's not so unrealistic. It's the Perkus-Javik correlation can be matched by that after a fashion. Walt-Drugan showed that. Now the thing is, if I calculate H0, it's got to be G0 times this small h. G0 times that small h. That just changes that exponential factor. So basically, you see, you can do the Fourier transform of H0 in your head. Instead of having just S squared over C0 squared, you've got the new exponential factor squared. Okay, so there we are. Now this is going to be a big advantage because it's so simple. But before showing you that, here's just one picture. I've chosen K as 0 for this picture, but I could have chosen another K. The lines would move a little bit, but they'd have exactly the same general appearance. This is actually a calculation done for a composite in which ρ2 is 10 times ρ1, okay? And it's a 50-50 mixture. P1 equals P2 equals a half. And this is the upper bound, this is the lower bound, And this is something in the middle, not a bound at all, just an approximation now, obtained by choosing rho 0 is the average of rho. And the reason for doing that is this picture makes it pretty clear anyway, that the small s, low frequency if you like, value of rho effective is just the average density. It's a well-known fact anyway. So if I've got to choose some comparison value for rho 0, I think that's about the best I can do at the moment. I don't really know how to do better. Okay, so that's that. But now let's consider the dispersion relation for a plane wave. I think you can see it, except I've got something in my way. That's it, I've moved it now. This is a plane wave, okay, a mean plane wave. And the dispersion relation is going to be this thing, comes from the equation of motion. And if I substitute our special case into that, it becomes the equation in this red box here, and gamma's defined. It doesn't really matter what the value is. But the thing is, that's a quadratic function in k squared, mod k squared. And the roots, if you like, are minus alpha squared and minus beta squared, because I like that notation. Okay, so I'm going to get out of this medium, and this is sort of not well known, I'm going to get two possible mean plane waves, what I'll call an alpha wave and a beta wave. And I choose the alpha wave to be one that basically doesn't attenuate at very low frequencies or small values of s, okay? And the other one does whatever it has to do. I think I've got on the next slide. This is frozen. That's it, good. Okay, this picture here is a plot of the alpha wave calculated with two possible choices for rho 1 and for rho 0. Rho 0 is rho 1 and rho 0 is average rho. Now, rho 1 is 85% of the medium, and rho 2 is 10 times as big, but it's only 15% of the medium. So you can think of this maybe as being a bit like a matrix with 15% of inclusions. So you would think that if I use the comparison material to be the matrix, the problem wouldn't be so complicated, and that might be a jolly good choice. But you see that at low frequencies, there's not much difference between the choices. But at higher frequencies, the difference becomes very, very big. As I say, I actually prefer rho 0 equals the average of rho. For one thing, if I didn't have one phase at a very low concentration, there'd be no hope of doing perturbation theory or anything, and I'd need to use some sensible comparison medium, and at least rho 0 is average of rho is neutral, and it's, as I say, I think it's probably the best I can do. If you look at the beta wave, oh, now look, the alpha wave has a wave speed, which is either this or this, I prefer the red one, and an attenuation, which is very, very low at low frequency, but it grows at higher frequency, okay? Now, if you look at the beta wave, it's the opposite. The starting value of the wave speed actually depends on the choice of comparison medium, but the attenuation doesn't depend on the choice of the comparison material. It's huge at low frequency. So you can visualize it at low frequency. You mostly get an alpha wave, and you'll get a beta wave that decays away very quickly. It'll just be in a boundary layer. And that's sort of consistent with what you know about homogenization. So I just emphasize, I actually prefer this average value for rho 0, but we'll just carry on a bit. Oh, yeah. Now I'm going to return to the original problem. I've shown you the picture again here. It's just the same, except that I added another wave into the top half because I know there's an alpha wave and a beta wave. Now think about it. We know we have continuity of displacement and traction. Now I'm only talking about mean waves, so really all I've got available to me to talk about is continuity of mean displacement and mean traction. That's two conditions. Unfortunately, I've got one reflection coefficient and two transmitted coefficients. So what can I do? Well, I can't find three constants from two equations, that's for sure. So I've got to basically get on and solve the problem. And I mentioned Manas to you that I'd found typos all the time in this presentation, and I wondered if I'd find any more during the presentation, and sure enough, look, there it is. At least there's one that I've noticed. Let's put it that way. Okay, suppose the medium now is of the type that I've just been talking about, but it occupies this half space, x2 bigger than 0, and it's bonded to a uniform half space below, and that uniform half space below is still going to have the same modulus mu, but it's going to have a density rho 3. Now, the characteristic functions chi1 and chi2, which are in the upper half space, have the value 0 when x2 is 0. And the additional characteristic function chi3 for the lower medium is 1 when x2 is less than 0, and it's 0 when x2 is bigger than 0. The variational formulation that I gave you still applies to this three-phase material, even though the material is not even statistically uniform anymore, because half of it is, and then there's another one underneath which is different. Anyway, the governing equations, the three equations, are these things here. Also, the basic representation for my representation for the displacement, the velocity, excuse me, in any particular realization is this, because here's chi r and pi r and chi r. If this were the exact pi, this would be an exact equation, but it isn't because I've only got this approximation for pi. Okay, and if I ensemble average that thing, I get the thing that's down here. So now what's in the red box, if you like, is a complete description of my problem. And what can I do about it? Well, as the composite only occupies x2 positive, I have a P1, P2, H. H is H of x minus x dashed, but of course it only works when x2 and x2 dashed are both positive. Now, if I look at my equations when r equals 1 and 2, I can manipulate those around as I did in the homogeneous, the infinite medium case, and get the stuff that's in this red box here, but it only applies when x2 is positive. The form of the convolution, the operator here, is still a convolution form, but it only applies when x2 is positive. The suffix c stands for composite, and it means that these functions are all restricted to x2 is 0, that's to say to the composite. Okay? That's it. That explains that notation. The c involved means restricted to the composite. On the next slide, you'll also see a subscript h, and h stands for half space, so that's restriction to x2 is less than 0. And so in that notation, the average of v is the average restricted to the composite plus the average restricted to the homogeneous medium. And of course, it has this representation, except that should be a v. My second misprint, I do apologize. Okay. And when r equals 3, the equation simplifies a lot because the psi functions with a 3 in are exactly 0. So I've got this exact relationship here in the composite. There's nothing really to worry about. I can sort of do some eliminations there. So now what you see is a summary of the equations. Okay. In the red box, you see a couple of equations which are true when x is positive, and another equation that's true when x is negative, and above the box you see something that's true everywhere. Okay, actually that's a problem of Wiener-Hopf type. Slightly unconventional, but nevertheless it's a problem of Wiener-Hopf type. If I Fourier transform with respect to I've got translation invariance with respect to x1 and x3, so I can transform easily. If I Fourier transform also with respect to x2, I've got a problem depending on whether I'm in x positive or x negative, x2 positive or negative, and correspondingly I'm going to get sort of partial transforms that are analytic in one half plane or another half plane. And as it's a matrix problem, a problem with more than one variable, that's a really hard problem to solve. except if I choose my special correlation function, exponential thing, repeated here, at least then this H thing only has poles in it. And there's a lot of hope then for solving the whole problem. I mean, I've said it's simple in principle. I'm going to make an admission here. To get from here to the next slide, more or less, which contains the answers, took me 4 months. This may be because I'm old, tired, and slow, but I do believe it's also an honest reflection of the fact that this is still a moderately hard problem. So anyway, look, there's a bit of notation. I'm going to keep the Laplace Transform notation with S in it, but S, in fact, will be put as I omega. Okay, I'm going to consider a plane wave with only a K1 and a K2 in it, not K3 is 0. And the wave speed in the lower half space is going to be C3, it's half space for 3, and that's just mu over rho 3 to the 1/2. And so K1 squared plus K2 squared plus K3 squared, which is 0, equals minus S squared over C3 squared. And so I'm using this relationship that's being pointed at, minus S squared over C3 squared plus K1 squared. That not in a bracket. Now the transmitted wave, there are 2 of them, but the alpha wave, there's an amplitude A to begin with, so it's going to be A times T alpha, transmission coefficient, times an exponential factor. The same K1 as before, because they've all got to be the same for to match up the plane, to match up the waves. But of course the K2 here is going to be different because it's got to correspond to the wave speed alpha. And there's the formula. Now, just to simplify notation and not have to think any more about K1, I'm going to change the notation here. And instead of writing alpha squared, every time I should write alpha squared plus K1 squared, I'm just going to call it alpha squared. So this, if you like, is a new alpha squared, different definition, okay? And then in Fourier space, H0 is going to become something else, which is going to have a K1 squared in it, 1 over K2 squared plus H0 squared. H0 squared is the sort of factor you had before, plus K1 squared. And the gamma thing I've redefined here also, in effect, it's got a plus K1 squared. So I don't even have to think about K1 anymore. So the notation at least is simplified to that extent. When I do calculations, all I have to do is remember to put the K1 in where you see it. Right, so that's the result, 4 months work. The great thing about it, the possibly surprising thing about it, is that it's completely closed form, as you see. And the notation isn't absolutely dire. There's one reflection coefficient, there's a T alpha, and there's a T beta. You could not find these from continuity of displacement and traction alone, because those equations are written at the bottom there. And actually, the T alpha, T beta, and R do satisfy those equations, but those equations, of course, are not sufficient to determine those quantities. So that's why we had to solve the whole problem. Well, basically, that's the end of the theory and everything. And now I'm just going to show you 1 or 2 results. The composite that I talked about first had rho 2 equal to 10 times rho 1, and rho 1 occupied 85% of the medium. Okay? I'm also going to choose rho 3 as rho 1. So you could, if you like, think of this as being something a bit like an epoxy matrix with lead inclusions in the upper half space, something or other like that. Of course, I'm not actually doing elasticity, I'm doing this acoustic analog, but still, it's something like that. And of course, I'm assuming the elastic constant is the same for any medium. Now, in these curves, the solid curves are the real parts of the transmission coefficient or the reflection coefficient. The dotted curves are the imaginary parts. That's it. Figure A is when rho 0 is rho 1, and figure B is when rho 0 is average of rho. I actually think that the second figure is the more accurate, but the reason I showed the first is that I did the simpler problem with just row 0 equals row 1 and also row 3 equals row 1 first. And so I had an independent check on the solution. And you see, there's not really any difference at all worth speaking about at low frequencies between this picture and the further one and the first one. But if you go to higher frequencies, there are terrific differences. So you see that something is going to come in somewhere. Excuse me, I've got a pop-up on my screen. I'm going to kill it. I hope I'm going to kill it. I've killed it. Good. Now, the next picture is the same configuration exactly, except, of course, I've chosen a certain frequency. Omega A over C1 is 0.3. And I've changed K1 so that I'm getting an angle of incidence varying. And those are the pictures. They're not all that interesting, but of course, it's a relief that I could calculate them, shall we say. Right, next figure is a little bit different. It's still row 2 is 10 row 1, but P1 equals P2 equals a half. So this is something that you definitely can't do anything with if you choose row 0 equals row 1. It's just hopeless, okay? But I can still do my game with any comparison medium, and so I'm going to choose row 0, I'm going to choose row 0 is the average of row. Okay, and what you see there is you see what you see, transmission and reflection coefficients, and here you see something varying with angle of incidence at omega A over C1 is 0.3. So that's a result that you couldn't get, I don't believe at the moment, by any method except the one that I've shown you. That's to say no one's demonstrated such a method. This next picture is just the same, except now row 3 has changed. Row 3 is average of row, as well as row 0 being average of row. But the thing is, average of row means that the lower medium is acoustically matched with the composite at low frequencies, and that's why the transmission coefficient starts at 1 and the reflection coefficient starts at 0. And if you look at the variation with the angle of incidence, well, you can see it. Okay. This is the same kind of thing, except now the lower half space has row 3 equals row 2. Okay, and I guess I could make no particular comment. There are the pictures, admire them or get bored by them as you wish. I'd like now to mention something slightly different. Lots of people, most people, the majority of any worker, when they're looking at metamaterials or composites, they'll have some method for computing a mean plane wave in a homogeneous medium. And if you're just looking for a mean plane wave, if you don't realize there's more than one, you probably won't look for more than one. And if you only find one and don't realize there's any more, the one you'll find is going to be the thing that corresponds to my alpha wave, because that's the one that isn't attenuating at low frequency, and it's obvious you'd be targeting from there. Now, if I only knew that there was an alpha wave and I didn't even realize the beta wave existed, I could then solve the continuity conditions and get an approximate expression for the transmission coefficient and the reflection coefficient shown in this box. I put a suffix A on this so you can see it. And the next figure is going to compare this approximation with the exact T alpha and R, which I've also put an alpha on, which I shouldn't have. That's 3 mistakes still in this. And you'll see it on the next slide anyway. This and this, the blue things, are the transmission coefficient, and they're in relatively thick lines. This blue line and this dotted blue line down here are the approximation. They're in slightly thinner lines, so that you see at low frequencies, if you neglect the beta wave, you're doing fine. If you have a higher frequency, you're doing not nearly as well. So basically, the second picture here is looking at the variation with the angle of incidence at omega A over C1 is a half. That's to say somewhere around here. So at least at normal incidence, this is normal incidence, is not looking bad. And it stays not looking all that bad, but it's just it's completely unreliable. It shouldn't be relied on at all. Look at what's happening at other kinds of frequencies. So that's it, except for making a few remarks to finish. The first is this: all my analysis is exact, but the equations that I started from are approximate equations because they rely on a Hashing-Strickman type of approximation plugged into the variational structure. There's something well known in wave theory called the quasi-crystalline approximation. It dates back from about 1952, proposed by somebody called Mel Lax. And in fact, these kinds of variational approximations are closely related to this QCA, but they're more general. Of course, I don't say that the realization that I've employed generates everything that can be generated with the QCA, but I could make modifications to build in to my structure anything that can be delivered with the QCA, except, of course, it would do. You can have any media. You don't have to have a fairly low concentration for it to work. Let's put it that way. Now, at low frequency, it's only an illustration, but you see it with your bare eyes. You see there's one dominant mean wave, one that doesn't decay much, and anything else that's there, in my case, it's only one other wave, it'll decay rapidly. By the way, if I as much as change the correlation function, I wouldn't just get one other wave. I'd get a lot, probably an infinite number. There would be a branch cut or something like that, instead of just poles in the basic function H0. Okay, but anyway, if you've got that dominant mean wave, you've found it some way, you can do an ordinary transmission reflection calculation, and at low frequencies it's fine, but at higher frequencies, well, it isn't fine. And that's going to tell you something about what's going to happen if you try and employ any local approximation for effective properties, because local approximations probably is going to mean approximating effective constants by just constants, not operators, and then you're only going to get kind of ordinary waves out of them. And if in fact the other stuff is important, you've just missed it for bad luck. So it seems as though with a boundary, you're going to have to think about things much harder and do more detailed calculations. Well, now, what else could we do?
John, we have about a minute left. That's okay.
Is that all okay? My watch says I've got 5, but there you go. Okay. I'll say this very quickly. One correlation, other correlation functions H. You could have modulus variations. You could do elastodynamics. They'd all get hard and a mess, but you could do them. I'll just remind you, item 4 here, you could interpret all these results for acoustics. And now item 5, I just want to say one last thing. All the mean disturbances in the medium decay away with distance from the interface. So what's happening? You think there's decay, but what's happened to the energy? The answer is, I don't know, and I wish I did know, but I think that I don't quite have the energy to do the requisite calculations, even though I know exactly how to do them. So with that, I'll stop.
Thank you. Thank you very much, John, and that was a wonderful talk. The floor is open for the panel to pose questions. Please feel free.
Sure, I have a question.
Oscar, go ahead.
Yeah, thanks, John. It's very nice to see that the structure that you have is formally, on a high level anyway, very similar to what appears in statics.
Yes.
On that note, is there anything known about realizability of the variational approximations that you have constructed?
I think the answer to your question is no. In this sense, nothing, no, not really. The thing is, the best I can do with this is if S is real, I can get bounds on these effective quantities as I've defined these effective quantities. But whereas in the case of statics, you can build composites that saturate the bounds for two-phase media. Nothing like that's been attempted for dynamic situations, although it would be very easy to do for laminates. But I don't actually think that it's been done, but it could be done. But for a more general medium, I mean, you'll realize it's much harder. And the statistics, I think, are always going to play some kind of role, except at very low frequencies. Okay, so that's all I can say about that, I'm afraid.
Okay.
Anyone else? Sorry, John.
Pedro, yeah.
Yeah, so John, you started to motivate this work, right? You said that there's a possibility of having this metamaterial type behavior where the incident wave could be refracted with a negative index of refraction, for example, right?
Yeah.
Now, you have two waves in this particular example. Can you capture that feature with this? Because you made this assumption about a very, very simple distribution, right, for the two-point correlation function.
No, I believe that it's too simple. I don't think elastic modulus mismatch would do it either. I don't think it would. But basically, you're going to get a good effect if you can get something like a resonance going. And there isn't quite enough in this, I don't think, to get a resonance going. I could be wrong, but I've not sort of found it. I was using a ratio of 1 to 10 on those densities, and remember, I've only done one correlation function. So under those conditions, I've not found any such thing. One would be able to think of a system with resonances and then consider how hard or it would be to analyze. I think if you're talking about just doing an infinite medium and looking for refractions, you could probably construct something and do the calculations. But then putting an interface in it the way I have and doing transmissions and reflections, well, it would be another piling on the complication. It might be possible to do it, but nobody would know. Not just me. I don't think anyone would know.
Thank you.
Okay. Someone else from the panel? Yes, Nick, please.
Yeah. John, wonderful, very, very difficult problem, amazing. And what I like is the fact that you show that, doing a problem analytically can teach you an awful lot. I really like that, especially the younger generation takes notice. A very naive question. The elasticity problem that you've done has a scalar displacement and a stress vector. Can we consider that as an antiplane shear? Are they antiplane shear equation, or
Yeah.
there's something different from antiplane shear? I'm sorry, I didn't.
Yeah, sure. You can do antiplane shear, except that the function h of r, which I chose, if I choose that exact same function in a two-dimensional context rather than a three, as you know, two-dimensional Green's functions involve Hankel functions or what have you. And so I'd end up with a more complicated kernel in my Wiener-Hopf equations.
Okay.
Formally, I could do something, no, for sure. When I said allowance for different functions h, that's the one that I had most in mind, truthfully. Just repeat this exercise, but for 2D. But it would have a major complication. It wouldn't just have two waves. It would have a main wave plus a whole bunch of waves that come from the branch point in the function,
Okay.
which I'd introduced. Yeah. So it's, yeah.
Thank you.
Norman, you unmuted yourself.
Yeah, okay. Let me ask a question. Clarification, first of all, John, I missed something. G3, that function G3, was that an explicit algebraic function, or was that?
Absolutely explicit. The wave speed in that medium was C3, okay? So basically G3 squared was S squared over C3 squared plus K1 squared.
Okay.
Did you hear that?
Yeah,
Sorry.
I did. Yeah, thanks. And that sort of leads on to the point that, from what I understand, often in these so-called, cloaking type metamaterials, you have quite a sensitive to spot frequencies, and it's not a very broadband phenomenon. What you're describing, I guess, here, as you commented, didn't have any resonances, and what you're describing is a response which is rather broadband in nature. Have I got that right?
Yeah. The frequency was arbitrary. Yes.
Yeah. Okay. So so in practical cases, when it's a random composite rather than a periodic composite, I guess one would expect a much more broadband response. So do people get a cloaking type behavior whenever it's a random medium rather than a periodic medium?
I don't know, because I don't know that anyone's really done it. I would suggest that what you get is maybe only approximate cloaking.
Yeah.
So you probably get, image reduction rather than image elimination over a slightly broader range of frequencies.
Yeah. That's been an interesting study, both theoretically and also experimentally.
Yes, there's something else too, and that is that if you want to construct a cloak, you're probably going to use local theory to construct it, even if you allow for some of this funny coupling in it. But you're going to want a graded composite. You're going to want something that is not just statistically uniform, and then you've also got some kind of dispersion or spreading coming from the grading, which, because the relations are inevitably non-local, which I don't think anyone's really been that concerned about. You know quite well, I know absolutely nothing about actually building things and testing them. So I can see these complications there potentially, and some people may have experience of them, but personally, I can only just comment that I expect they're there. Okay,
thanks, John. Great stuff.
Agnes, would you like to say something? You have to unmute yourself, Agnes. Sorry. Yes.
Yes, I have a question, in fact, that concerning the meaning of this wave in the high frequency regime, because usually when we speak about effective waves, say, we have in mind the coherent part of the signal, which is the part which is repeated for each realization, and the ensemble average aim to faire disparaître, to cancel the incoherent part of the signal. You see what
I think what you're referring to is the fact that mathematicians usually calculate the ensemble average, and experimentalists can never easily observe an ensemble average. They're more likely to see a spatial average, and the two things are not identical. And there's no way around that. That's the truth.
They become in some sense identical or comparable, say, if there is some coherent part, a strong coherent part from one realization to the other. So my question is, what do you think? Do you think that this coherent part exists in the high frequency regime, where one modification of the location of the scatterer, for instance, if you have in mind a purely periodic case, and then you move a little bit, so you change the realization, you can observe strong modification of the scattering.
You can, yeah. I mean, it's a bit like the twinkling star problem, isn't it? There isn't anything that's going to stick around either temporally or spatially in the same, just be uniform, as it were. It won't be fixed in time, or in the case you're talking about, if it's a harmonic wave, you're not going to see something fixed in space. But this is just an intrinsic problem, I think, with looking at mean waves. If you look at mean waves, you get some information. It's good information, pretty good information at low frequencies, and at higher frequencies, I don't know that it's so much use at all. The simplest thing I can think of at higher frequencies is to calculate the energy flux. In other words, do transport theory in some form. And I alluded to that slightly in my conclusion number 5. I don't know, for instance, how much energy my medium that I've got is going to reflect back into the half space. You could measure it, but I can't predict right now what it would be because I've not done the calculation, although I do know how to do it, at least in this approximation. That's why I say I think it's interesting. But I agree with you absolutely that knowing the mean wave is not at all everything you want to know.
Okay, thank you.
How about the other panel members? Kim, would you like to say something?
Yeah, maybe I have one question. When you have, let's say, a periodic medium, and you stick this periodic medium to a homogeneous one, when the wavelength of the incident wave becomes comparable to the size of the microstructure, you can have several order of diffraction. And do the multiple mean waves that you find are related to the fact that the wavelength of the incident wave becomes comparable to the size of the distance between the scatterers.
Yes.
And is there a link between what you can find in periodic medium and what you find in random medium?
There's a similarity, but the difference with a random medium is, look, I don't know. It may be you can, I'm sure you must be able to make some random medium so that you had 2 mean waves that didn't decay too quickly and some other junk that decayed very quickly. In the example that I showed, it's an exceedingly simple example. I had one mean wave that didn't decay quickly at those low frequencies and another one that did. But you see at higher frequencies, the whole thing is confused. But those 2 waves were the same sort of size, and this is related to the point that Agnes was making. What are you going to see? It's not so easy. So yeah, the difference with the periodic medium is that everything can be analyzed, not only the propagating waves, but also the evanescent waves, of which there is always, I think, always an infinite number. But you're in more trouble with a random medium just because you don't have so much precision, even in principle, to be able to describe the wave. This is why I thought it was a bit of a challenge, and I tried to make a small start on it. That's all.
Okay. Thank you.
Okay. Would anyone like to make any more comments? Okay, we have one question from the audience. Art Goer, if you would like to unmute yourself, please go ahead and
Hello?
ask your question.
Can you hear me?
Yes, I hear you.
Oh, hi, John. Hi. Thanks. Great talk. Been meaning to see that. So I guess my main question, well, I have many questions, but for another day. The fact that you have 2 effective wave numbers is very interesting, right? You'd think it was something inherent about averaging this kind of microstructure. So my question is, how do you think this sort of analysis carries forward to other material geometries? So you've shown for a half space. How about for a sphere? How do you think you'll find this? You should be able to find the 2 same mean wave numbers, I imagine.
If you're talking about my 2 waves, those are actually waves that will exist in an infinite homogeneous medium. I wouldn't have known in advance even that the only things I would see anywhere, even close to this interface, this plane interface, those two waves and nothing else. But at the very minimum, you're going to see those. In the same way, you would see these if you had a sphere of this stuff, and if the sphere were big enough, sure enough, this would be what you'd see. If the sphere was small, then you've got, I don't know, whatever modes you get in a sphere, but whether the modes are, possibly the modes will only be made up by these 2 waves bouncing around, or if the sphere is small enough, you know, it's much more detailed. Looking at the ensemble average would be virtually a waste of time if the sphere was small enough. This is even a problem in static problems. If you've got a small sample without very much in the way of representative microstructure, if it's small enough, there's nothing to average. You've just got to solve the problem, and it's a mess. If it's slightly bigger, you can solve the problem, and you can demonstrate that outside of a boundary layer, it looks a bit like homogenization, and so on, and so on, and so on. And in dynamics, it's just worse. Definitely not a problem I'm going to do. I'd like to tell something. I mentioned that there is about one other solution to a problem of this type, and Art is at least partly responsible for it with co-authors. And his system actually had his half space with the same properties as the matrix, not different. And it was at relatively low volume fraction. It used the QCA, and it actually adopted a multipole approximation rather than my simple single pole approximation, what it amounts to. And to that extent, it's more general. They discovered also, that there was not just two waves, but an infinite number of waves in that context. But I believe, Art, you'd be able to confirm this, that the explicit calculation that you did, the nearest thing you got to an explicit calculation, was actually looking at what the monopole contribution by itself would give. But I think that it's basically you and I that have got any solutions at all, I believe.
I think so, yes. I'd also say that our theory gives mostly two wave numbers, as you do. So we're kind of agreeing
Oh, that's
on
very
that.
good. Okay.
It's
yes.
mostly two. We've never found a circumstance in which more than two dominates. The others, as you say,
yes.
are evanescent.
Yes. Yeah.
And
but
yes,
again,
you're right.
Again,
in terms of
my results use an exponential correlation function. Yours use something different. So I think neither of us is all that easily well equipped to make absolutely general statements yet. Is that right?
No.
Yeah.
Yes, absolutely.
Yes.
And you're right that explicit was for in terms of a simple formula for everything, we only did monopoles.
Yes.
Oh, we can go beyond. We can use the same correlation function you do as the exponential. This exponential,
of course,
if we want to do.
Naturally, yes.
But we haven't actually done that in detail anywhere.
Yes. You can see very well why I use it, can't you?
Yes.
Because of the getting poles and nothing else. Yeah.
Okay, we can take one last question from Valery Smyshliev. Valery, you can unmute yourself.
Yep, yeah. Okay, hello, John, hi.
Hi, Valery.
Can you hear me?
No, I can't, I'm afraid, but I can hear you loud and clear.
You cannot say, okay, you can hear me, good, great, okay. Great talk, John. A question, so your predictions sensitive to the choice of the comparison medium, obviously, right? And as you know, right, from my own experience, would it make sense to try and choose the comparison medium in a sense self-consistently under this scenario?
It very well could be, I imagine, but I haven't tried to do it.
Right.
But yeah, that would be possible. Take hold of that simple formula for rho effective and sort of make up an equation from it. It would be easily possible to do that and see what comes out. And I do not know what comes out. You can tell me tomorrow.
Okay. All right. Okay. All right. Thank you very much.
Okay, so that's all the time we have for the questions. Thank you very much, John. And if you would like to say something, please go ahead.
Not much, just thanks for turning up and asking questions. And hope I'll see you physically soon.
Hopefully soon, yes. Goodbye, everyone.
Thanks very much.
Thanks, goodbye.